Uh, First of all, again, welcome everybody to uh, the webinar. My name is Yihong, and I'm the Business Development Manager at East 101. I'll also be the moderator for today. So good evening. Thank you so much for coming. Just to run through some of these uh, experience, sort of quality of life things. If you pin the presenter, Abdullah, as the main screen, that will ensure that um, the, the, the slides should show up in the right window. So if you pin and you click on that particular window, you should see um, uh, these slides, and when you fit to frame, they'll come up to the right ratio for the best viewing experience. Muting and turning cameras off will help to save bandwidth so that we get to present in a smoother rate for your experience. And yeah, so moving on to the next slide. Oh, I need to request control. Abdullah, could you grant me control? So today we are going to be talking about how heat management prevents corrosion under insulation. I am assuming that some of the attendees might have encountered some issues with heat management or CUI yourself. And if you have, feel free to tell us more about it in the chat. We are excited to share our experiences, hopefully answer some of the questions that you might have. If you like our content, we hope that you will help us by continuing to spread the word. We'll have more of these webinars in the future. For those of you who are new to East 101, we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services to the oil and gas industry through process simulation technology. A bit of background, we were founded in 2003 by engineer Rafael Elias, who's also in the webinar. And we have offices mainly in Kuala Lumpur, strictly speaking Shah Alam, but also other places around the world where we have some presence. Our track record includes projects which cover transient or dynamic simulation-based engineering services for design and troubleshooting. So you'll see the list over there: facility-wide control, blowdown, HIP studies especially. Flow assurance, which includes pipeline study and flex hydrate management. Operational assistance, you can see, covers some of the troubleshooting aspects and up to operator training simulation, which is a field that we hope to grow. And process simulation training, which basically based on our experience, we can conduct training sessions that help engineers improve their skills with this technology. Our clients range from engineering houses to even the asset owners, as you can see, Shell and Petronas are among them. So if you have any inquiries, please contact myself, Zihong, or my colleague Avinash at the numbers and the email address shown. More information is available on our website, www.east101.com. As mentioned earlier, this is not a one-off. We are hoping to continue a series of such webinars, and we hope to cover a wide range of topics from upstream process design to downstream and refining, monitoring, surveillance, as well as analytics and AI. In the past, we have covered those topics before, and I'm not sure if the recordings are still on our website, but we can make sure that you have access to them if you're interested. Just drop us an email. Let us know. Right now, the webinar is planned to take place monthly, every second Wednesday, and same time, 4 p.m. to 5 p.m. Malaysian time. So to recap, in case anybody dropped in after the initial introduction, we hope that participants stay muted. And any questions should be typed out in the chat box. We'll get to them at the end of the session. There's going to be some time for Q&A. And if you miss anything, the recordings will be available on the webpage. All right. Today's speaker is Mr. Abdullah Azhar, who is one of our more experienced process engineers at ACE 101 with 5 years of process simulation experience. Abdullah graduated from the University of Technology in Malaysia with a BEng in chemical engineering, and is a registered member of BEM as well as associate member of IChemE. As you can see, Abdullah has a strong background in process simulation, having worked with us for that long, pretty much a specialist, and he's done everything from upstream to downstream. And I would say, working with him, he's a very valuable asset at this one. Without further ado, let me invite Abdullah to tell us more about how heat management prevents corrosion under installation. Abdullah, please.
Okay, thank you very much, Zihong. Good morning, evening, or afternoon to everyone, whichever place that you came from. Thank you very much attending for this attending this session. So today I will be talking about the heat management. So how does heat management assist us in preventing the corrosion under insulation problem? So my name, as Zihong introduced just now, I'm Abdullah, process engineer from ACE 101. So before we start, let's have a look at some of the agenda for this session. So I will be talking about some of the introduction to the heat management and the problems regarding the CUI or corrosion under installation. And then we can have a look at the analysis, like how we conduct the analysis and what kind of things that we have to look at when we do the analysis. And then I will talk about the outcome of the study. Based on this study that we did, what is the resulting outcome that we find out. Okay, so let's start with the introduction section. So typically when during design stage or when people start to look at designing a chemical plant or topside facilities, there is a stage activities involving heat conservation evaluation. So doing this is typically we evaluate how we can conserve the heat to optimize the utility consumption and also to control wet formation. So by looking at this, there is a requirement on piping insulation. So common practice, people always use conservative approach. So this may lead to installing the installation where it might not necessary or maybe have negligible impact on the process. So if this is the case, then it can increase the potential corrosion under installation risk. So that can be quite troublesome. So what is corrosion under this insulation and what's the problem with it? So corrosion under insulation is typically occurs due to the fact that your insulation, it can trap and accumulate your moisture. So if you look at this image, over the time when even you perfectly install the installation, over the time you might trap some of the moisture, and if the moisture accumulate with a correct condition, so usually when things corrode, so you have iron, you have oxygen, and you have water. So there will be a process, some electrolysis process where your iron oxidize. So that's why your iron become a rust. So that's iron oxide. So if you can see here, where you have oxygen, water, and everything, you might have corrosion under installation. So this is more severe than the corrosion of uninsulated equipment piping. If you look at the image, it's quite worse if you open up the insulation, because of your corrosion under insulation is not visible and goes unnoticed for a long period of time. So since it's under insulation, you can't see it, so it can be dangerous, and this may lead to losses of containment and causes fire. Even worse, it can cause fire. So this is something that you want to avoid when we operating a chemical plant or topside facilities. So this is some article I found from insulation expert. So over here, if you look at the fact is that the highest incident of leaks in refining or chemical industry are due to CUI and not process corrosion. So CUI is this is the highest incident of leaks happen in the chemical industry. So most piping leaks, which is 80%, occurs in the diameter smaller than 4-inch nominal pipe size. So if you have small pipe, that is most likely it can have a piping leaks due to the corrosion under insulation. And if you look at the final point, they said that between 40 to 60% of piping maintenance costs are related to CUI. So there is huge amount of cost, total cost when people do piping maintenance, which is 40 and to 60% of the total piping maintenance cost. So now we know that it's an issue in daily in most of the chemical plant or topside facilities. So let's now we want to ask ourselves, so is it possible to remove the piping insulation? Let's look at specific case here. We are looking at the existing topside facilities. So these are the factors that we are considering when we ask ourselves about this question. So first is maintenance cost. So how much maintenance cost can we save if we remove the piping insulation? Next will be the heating and cooling cost. So let's say you remove it, you save the maintenance cost. How about the heating and cooling cost? Do you need to, since you are removing the insulation, which the purpose of the insulation is to contain the heat. Now you might lose the heat, then you might need to add a heat. Do you need to add more cost on that? How about safety? So if you remove the insulation, if the pipe will the pipe become too hot, or if you remove the insulation on the cold pipe, so you might observe some sweating on the pipe. So and you have drippings on the floor and everything. So that is a safety factors consideration has to be taken into account when you want to remove the insulation. And then the process of operability. So since you are removing the insulation, your temperature might change. So how does that impact on your process? So these are the things that we will need to look at when we want to remove the insulation on the existing topside facilities. So this is some typical flow diagram that I found. This is done by BP. So over here they have a flow diagram to evaluate what the heat conservation. So when you go to here, you see can heat input be increased or for the heat loss. So if it's no, then is there any operability reason for keeping insulation? Then if it's yes, then keep the insulation. If it's no, then is the insulation required for personal protection? So if it's not, then you can remove the insulation. If it's yes, then maybe we can replace it with insulation with burn cage or coating. So sometimes we can look at when it's required for personal protection, we can maybe look using a cage instead of insulation with cladding and like raw wool and typical insulation. So there is a bit of the instruction. So now let's look at the analysis. So let's consider the analysis that we done is considering that these three systems. So this is the production separation system. So if you look at here, the highlighted orange color is where the insulation located. So in this case, we have a heat tracing insulation. So where they put heat tracing downstream liquid outlet of the production separator and pump outlet and the minimum recycle flow line and going to the cooler. And then we have a compression system, like typical two-stage compressor. So the insulation location is as highlighted in the gray line. So in this case, it's a thermal insulation and also acoustic insulation because for the gas it's quite noisy. So that's why they put acoustic insulation. And then for this one is a glycol regeneration system. So the location will be in the red highlighted lines. So this is mainly to conserve the heat for thermal insulation. So all the lines are located so that when you flow from glycol contactor and sending back to the glycol contactor, the heat is conserved. So because in glycol revolver you are using heat to boil off your water. So this is where they place the insulation such that you don't lose too much heat and you can minimize the heat requirement at the glycol boiler. Even before you look at this, you have to understand like the science behind it, the phenomena behind it. So this is the typical piping insulation. So you have a cladding out at the outermost part of the piping, and then in between you have insulation material. So this can be rock wool or gel or any other type of insulation material, and then you have your piping inside here. So this is the typical piping. What happens is if your piping is exposed to ambient air, so you have a few phenomena happen here. So first is convection heat transfer between your ambient air to the outer layer of your cladding, and then you have conduction heat transfer between your outer layer of your cladding to the inner layer of your piping, and then you have convection heat transfer between your piping inner layer to your fluid. So this is typical like kind of phenomena happens when we're dealing with heat transfer inside the pipe. So let's look at each and every phenomena. What kind of equation behind it, and how can we calculate the heat loss at these three particular section. So for convection heat transfer between the outer layer of the piping wall or like metal cladding to the ambient air, typically if you look at this, I don't want to get into detail on how the equation works, but if you look at the equation, so this Q heat loss is equal to heat transfer coefficient times area and difference in your temperature, meaning your ambient air temperature and your surface temperature. So it's a function. If you look at here, there is a function. There's a heat coefficient, which is a function of Nusselt number. So if you look at here, this parameter, it's calculated based on your velocity, your diameter, and then your Prandtl number, which is viscosity of your air. So all of these parameters will impact on how your heat loss and your piping heat loss. So in this case, what we need to do is we have to look at the conservative approach. So if you are conserving heat, meaning that the pipe has to be hot, meaning that you need to select like in this case we have to look at the ambient temperature, because we are looking at your velocity, right, which is the wind speed, and then your temperature, right, the free stream temperature. So this is something that you have to consider the most conservative approach, meaning that if it's hot pipe, if you need to keep it hot. If you are removing the insulation and the piping can become cold, so then we have to select the temperature such that it can give highest heat loss, which is the lowest temperature, and the wind speed has to be highest wind speed. If the piping is cold and you need to keep it cold, then you can select the temperature, ambient temperature, to be high. So those are the things that has to be considered when we are doing this analysis. So this is some historical data from Malaysia ambient temperature. So if you look at the first graph, over here I have temperature from January to December. So this is some general data that I found at Weather and Climate website. So if you need to do this analysis, you have to confirm it with the site or the client, like what are the numbers that you should use, because in reality we can have different temperatures at different locations. This is some general number at Malaysia. So the temperature can be, the high temperature can be around 32 degrees Celsius, and the minimum temperature can be around 21.5 degrees Celsius. And the humidity doesn't change that much, it's around 80%. And then water, if your pipes is submerged in water, so this is the typical profile for the water temperature. And then the wind speed will be around 2 meter cube per second, and then can be lower than that. So this is some of the data that you have to consider when we are doing the heat loss calculation. So now let's look at the second phenomena, the conduction heat transfer. So in this case, it's a function of your piping length, your radius, your piping radius, and your thermal conductivity. So this is the conductivity that tells how well your pipe or your insulation material conduct heat. So just some example here, you have steel, so the conductivity is 50 watts per meter Kelvin. If you look at rock wool, like the typical insulation material, it's 0.033 watts per meter Kelvin. So meaning that's why people use rock wool as an insulation material, such that the heat doesn't transfer out or into your system. So if you have a multi-layer, you can have different conductivity and different radius. So that will be used in the equation to calculate the heat loss. In this case, if you look at this diagram, you can consider this you can consider this as a resistant. So let's say your heat. So typically heat will transfer from hot to cold, hot side to the cold side, right? So you can consider as this is the resistant. So let's say your heat if your piping is hot, then your ambient is colder. So if the heat want to travel through your piping material, there is, like in this case, this is a simplified equation. There is three or four type of resistance. So, and then last one will be the convection heat transfer inside the pipe. So this one, it's based on your flow regime. So if you have laminar flow, so the heat transfer, it's based on this equation. And if you have turbulent flow, then it will have different heat transfer. So this kind of equation is if we embedded behind, in this case we are using process simulator. Like any process simulator will have their own heat transfer equation. Not that you have to remember this equation, but you have to know that what kind of heat transfer that it's being used, it's being done behind your process simulator. Either it's span high seas or unisim, or maybe symmetry. So those are parameters that it's being used, so that you know that what are you doing when you do this analysis. Yeah, so overall you can have like something like this, all the temperature profile. So you have high temperature, then you go down, and then after that you further go down and further go down. So this is based on the resistance. So this is one resistance, second resistance, and third resistance. So that's how your heat loss being calculated. So now the objective of this study, we want to evaluate if the existing insulation it's still necessary. So if it's not, is it possible if we can remove the unnecessary insulation? So by doing this, there is few steps that's being done. So first step is data gathering and consolidation. So in this case, we went to the site and gather the pi data and then consolidate all the isometric check the insulation if it's there. Is it perfectly insulated? And then maybe we can measure some temperature so to see that whether the insulation is good enough, whether it's still effective, whether it's still prevent the heat loss, or if the insulation is not useful anymore. And then trace the line and check the compressor data and all the take the fluid characteristic. After that, once we got all the data, and then we construct the model. So by utilizing simulation tools, we construct the whole topside facilities model, and then by modeling all the piping in detail, with the elevations and the length, and then all the fittings, elbow, T, and everything. After that, we run a case study. So with and without insulation, we did the case study to check if we remove some insulation, how does the system behave? How does the temperature change around the process site? And then we analyze the results to see whether it is feasible to remove the insulation, or what are the impact if we remove the insulation at some part of the process or the whole part of the process. Yeah, so why I'm telling the equation, everything, the equation earlier, because of we would like to avoid garbage in, garbage out, because the quality of information coming out cannot be better than quality information when in. So if you don't put proper data that goes into your simulation, obviously you will get not a very good result. So this is something that you have to remember when we doing this kind of analysis. Yeah, so now let's look at the outcome of the study. So for first one will be the gas compression system. So we noticed that when we remove the insulation, the minimum difference, like the highest difference that we observe is at inlet of the second stage compressor, so which is 3.7%. So that is equivalent to 3.9 degrees Celsius. So we noticed that when we remove the insulation, so the highest difference that we observe is 3.7%. And then that will result also the duty requirement reduction, 4.3% duty requirement. So meaning that since it's colder here, so your after cooler duty reduced by 4.3%, which is around 285 kilowatt. Next would be, so the minimum temperature does not drop below hydrate formation temperature during normal operation. So since now there is more heat loss when we remove the insulation, the minimum operating temperature, it doesn't drop below hydrate formation temperature. However, we noticed that the operating temperature might drop below hydrate formation temperature as the ASV open for a short period of time. In this case, we noticed even with insulation, they might have issue with hydrate formation at downstream of the anti-surge valve. So because of, since you are dropping pressure from high pressure to low pressure, then you may have JT effect and your temperature drops, and it can drops below your hydrate formation temperature. For oil stabilization system, we noticed that the temperature difference between case of with insulation and without insulation is 4.2%, so which is around 2 degrees Celsius, 2.7 degrees Celsius. And then in this case, without insulation, at normal operation, so this we are talking about the normal operation. Without insulation, it drops to 60.8 degrees Celsius. However, the wax appearance temperature, it's around 43.5 degrees Celsius. So that is still higher than, so your operating temperature is still higher than your wax appearance temperature. But however, during shutdown, so this is the cool down curve. So if you look at the green color line, it's a cool down curve with insulation, and then the blue color line is the cool down curve without insulation. So so if you shut down your oil stabilization system and you leave it not running for a long period of time, the time taken for the fluid temperature to drops below wax apparent temperature, it's around 27 to 37 minutes. So this is at one composition. We also looking at the wax apparent temperature at different composition. So there is two type of fluid composition that we check. So it can take around less than 40 minutes to drops below wax appearance temperature. However, if with insulation, it can stay without forming a wax for around 90 hours to 30 hours. So this could be an issue if the insulation need to be removed. For glycol regeneration system, the minimum temperature observed is at inlet of the heat exchanger, second heat exchanger, which is around 13.2 percentage, which in terms of temperature is around 9.5 degrees Celsius. So originally with insulation, the temperature here is around 72 degrees Celsius, but once you remove insulation, your temperature might drop to 62.3 degrees Celsius. With that reduction of temperature and heat loss, the D3 required at the glycol boiler increased by 9.7%, which is equivalent to 34 kilowatt. In this case, when you look at the design, the reboiler design, it can still meet the duty even we remove the insulation. But during startup for glycol regeneration system, with insulation, since there is no heat loss, you can at initial temperature, at ambient temperature, your glycol system initial temperature of around 22 degrees Celsius. It takes around 3 hours to reach operating temperature. This is for startup. And then when without insulation, it might take 4.5 hours to reach the operating temperature of around 195 degrees Celsius. So in this case, we have to check with operators, see whether this is something that an issue or if it's something that they can just wait for when doing the startup. Yeah. So there is things that we found out, and the key finding here is removing insulation has minimal impact on gas compression system. So it is around 4.3 reduction on discharge cooler duty. Removing insulation at glycol regeneration system may result in higher reboiler duty requirement, which is 9.7, and longer startup time. So in this case, operator has to decide whether this is something an issue or not, or whether it's still manageable when they are operating their plant. And then removing insulation with heat tracing at the oil stabilization system. It may cause wet formation may result in wet formation at shorter period during shutdown. So during shutdown, wet might form at shorter period when the insulation is removed. So all of this study was did only for thermal point of perspective in term of like acoustic, like the noise. That is something that we have to check with the mechanical team or the piping team. So in conclusion, the study can benefit us in terms of we can ensure safety by minimizing the risk of hazardous leak due to CUI. Also, we can save costs by reducing piping installation maintenance requirement, and we can improve decision making by eliminating guesswork by quantitative analysis based on the real operating data, and we also can improve future-proof asset by enabling digital twins technology with a rigorous first principle dynamic model. So this is something that can benefit plant operators when we do the study. Yep, I think that's all from me. Thank you very much. If you have any question, you can put it in the text box. And I will pass back my control to Zihan.
Thank you. Thank you. Yeah. So once again, thank you for hearing myself. An insightful training session. And for those of you who thank you for attention. If you have any questions, we can ask you. Yeah, before we get to the Q&A, just a reminder, if you have any queries about studies that we can do, if the content that we've shared today has triggered some relevant work that you might be working on and you want to discuss further, please reach out to us, Hong, Avinash, my colleague, and check out our website for the recording of the webinar once it's uploaded, so that you can review if you have any parts that you want to share or go over. And we are also on LinkedIn, although the link is not there. But if you follow us on LinkedIn, you would get the latest updates on anything that we're doing. And so, does anybody have any questions at this time for Abdullah? Or if you do have any questions, feel free to type them out in the chat box. And we'll read it out. If anybody has questions that they'd like to ask later on, please book. Once again, you can refer to our contact numbers or the email address to just shoot us an email about anything, to find out more about IS101, what else we can do, maybe some troubleshooting that we can help you look at. And with that, I think we'll call the webinar to a close. Thank you all once again, and look forward to the recording. Thank you.